Are we ready? Jumping in. Thanks for being here on a snowy morning. Hopefully, main thing is keep yourselves safe. Like if it's not safe to come in, we do record every lecture. It's different than being here in person, but keep commuting safety as #1 priority. No reason to put anyone at risk to get here to do some engineering. Cool. So last time we were taking a look at like weightlifting. This time we're going to look at luge. So like what are the forces involved? Do you know what a luge race is? Some guesses. Yeah. Yeah, so it's kind of like bobsledding, but you're laying down on just one little sled. So we have this image of someone riding their luge, and the head is like at the back of the sled, like in a helmet, and the feet are pointing down below, and they're flying down the ice. I think average speed is something like 40 or 50 miles an hour coming down these slopes, which is pretty terrifying, like to be just on ice skates moving that fast. But we're trying to create free body diagram for forces involved in this sport, in this maneuver. So I want to see like where you think that leads. And Friday, we were talking about like how free body diagram is different depending on what question you're trying to answer, or like what you're investigating. So why draw it one way versus another? Think about like what would you do with it? What forces do you want to consider? Why those forces? Why are they pointing in that direction? That's kind of the questions that we're trying to build here. Yeah.
Since it's on ice, could we assume that there's next to no friction force?
Ooh, yeah. Does ice mean no friction? That's a good question. Sorry?
Like very negligible.
Very negligible. So in terms of like sliding friction, so once you start sliding, there's like a dynamic friction. It's different than normally when we think of coefficient of friction. It's usually like, what is the static coefficient of friction? Like how much force do I need to get this thing to slide. But once you start sliding, it's even lower than what it took to begin sliding. And dynamic friction for ice, I've slipped on the ice like twice now through this winter. There's so much ice, it's ridiculous. Like my knee is all bruised up. I'm a mess. But dynamic for like steel on ice, like ice skating sort of dynamic friction, it's about like 0.005, something like that. So 0.01 is not a bad, like if you're trying to be, say like, oh, well, it's kind of a high, like it's a rough ice, going out on a pond and ice skating. Like there's no Zamboni out there to make it smooth, but really, really small. So maybe that is negligible for like the things that you're considering, but it depends on what you're trying to consider. If you're like, this force is, yeah, again, that's up to you, but ballpark, it's 1% of whatever the weight of your thing is. Yeah. It's always nice when you can just say, this force, it's there, but it's 0. Like, not for me. What are you thinking? Oh, okay. So you have like force of friction going up like a curve. Oh, is it going too far? Okay, that's what I'm familiar with. So is the sled like going down a curved ramp, almost like a half? Yeah. So is it coming at you, or is it coming? This is but that. Okay, so it's sliding towards me. Yeah, this way. Would you try? I had trouble drawing 3D diagrams, so usually I'll have like 2 front and a side view. Okay, so I've got to do the 3D. I can't express that.
I just had a question.
Oh, interesting. So it's normal, are the normal friction forces at an angle for each other?
I guess so. I guess the normal force surface curves, I guess.
Okay.
It's not like it's kind of directly on. And then the force direction.
Yeah.
It like directly opposing.
Okay. That one, it looks like kind of side views, right? Yeah, like a isometric.
We used to have our engineering class. It's like all the.
So the only thing there is usually if normal force is pointing one way, friction is normal to that. Yeah. And that part is if you're thinking.
I think I was trying to do 90. I think I just didn't.
Okay, that's okay. Yeah. It's not a drafting thing. Okay, yeah. Oh, so like gravity ready for it, you're saying. Okay. Is there anything else slowing it down? Like friction? Air? Okay. I just feel like
Yeah. So is there, what causes it to speed up? Oh, is it going down? It's like, yeah, so at least like the race starts up somewhere, it goes around a bunch of curves and then low and low. I'll pay you $50 to do that. Fine. Give it to me, I'll upcharge Ryan everything with just being able to. Okay, yeah. I know so many of those. Like, you want to sit with us? I'm creating a section. I'm waiting out. I'll skip it. I'll come. I'll do after my other brother. I'll see if I at least like I have to. I'll hold you to I've got right now about my now I'm a score and no, it's just us. It's probably not even but we're not gonna sit right next to each other. I think they're so handy. Just the bottom section. Just the bottom section. That's all I'm St. John's. They're ranked top 10. I actually think I like we do. Yeah, but was it St. John's? So that's who they play. Like, he totally would not see it from my house. No class on He's gonna wake up. I'll bring you to I'll wait for I'll wait there with my can. You not like The rest of my classes are just hard enough for my you were so I love this music, but there's no
All right. So we're building like a couple of different approaches to this. One of the things that is hard, I struggle with this of like trying to draw a three-dimensional free body diagram, because like this versus that, like they all look like they're all it's catching up. It all looks like it's just pointing in the same direction, right? Like it's hard to get the idea of 3D out of that. I mean, I could put like what are the components of it or something if I want to start like creating some kind of view, but I'm not very good at it, so I just don't bother. So instead, like if I'm trying to draw this person and I want to say there's like normal force from that curve, right? So they're coming around a curve, there's some kind of normal force, and then I want to say, all right, well, there's also like weight of the person going down. So I'm keeping everything like in 2 dimensions, like as if I took a cross section and I'm just looking there. So people are, one thing that I saw was like trying to draw like friction somehow pointing into the page. One way that I do that is like force of friction is like an X means that it's going into the page, something like that. And then a circle is like coming out of the page. That's what I learned, was like an arrow leaving you, you see the tail of it, an arrow coming at you, you see the head of it. And then also, we could say like some kind of force of drag coming that way. And then if I'm really concerned with like trying to get everything right, then maybe I would also have like a side view. And this one, yeah, this one's hard to do, like the side view. How do I want to do that? Yeah, this one's hard, right? Because even the normal and the weight are not, it makes it look like they're put together somehow. Yeah, I don't really like that second drawing that I did. Just don't like it. All right, but let's take a look at this for a second. Why? Oh, sorry, go ahead. So I was thinking of this person coming towards me. Yeah. So like they're coming around a really big curve. So then if I look at like the top view of it, it's as if they're like going around this curve, and the ice, at least the, oh yeah, let's do this. We have like a big ice curve that they're coming around. If I look at the top view, that's what that's what I was trying to interpret from some other drawings, and that's kind of what I saw. Was there a different thought on? Yeah.
Oh, what was this one? Can you use
I use F. So F is like force of friction, and then FD is like force of drag. And the reason I always say like force of drag rather than like friction due to air or like fluid friction is that force of drag has a very specific definition. Get rid of that.
So was that also pointing to the finger?
And that one is pointing like it. Force of drag always opposes your motion. So if I'm moving forward, force of drag is backward. If I'm moving to the left, force of drag moving to the right, like pushing to the right. It's always something. So the direction is always like in your velocity divide by your wherever your velocity is pointing, force of drag is opposite that. So that's why I usually write it as like, if I want to say like there's something other than friction slowing it down, I always say like force of drag. Because that one, I know the definition, you get to look up those constants. There's CD, there's density of the air, there's cross-sectional area of this lycra body. So thinking about like this free body diagram, why were you considering, what is this answering? Why would we use this free body diagram rather than something else? Yeah.
Why is the top one?
Yeah.
Maybe so you can establish a better coordinate system.
Okay, trying to pick a coordinate system. Okay. So maybe you're just like sort of exploring, trying to figure something out. So here's another one that I saw. And I think this was kind of what I had seen. Have weight going down. Normal force is normal to whatever slope this thing's on. And then force of drag, and then maybe a force of friction. So this was another one, all two-dimensional stuff, right? Like we're not worried about coming around corners and like vectors in and out of the page. So why do it this way versus that way? So here, this is like option A, and here's behind door B or door 2. So why A versus B? What are we trying to answer with these questions? Or sorry, what is the question that we could answer with these free body diagrams? This one looks easier to deal with, right? B. Why not just always draw free body? Why not draw the easiest free body diagram that we can always draw? And then just ignore friction, so set that to 0. Ignore drag, set that one to 0. And now we've got normal force and weight. Like, all right, cool. This is much easier. Yeah.
Seems like it doesn't take into account the centripetal motion, like going around the curve.
Okay, so here we're not actually considering like curves, right? Like the fact that when you go around the curve, you're going to go up the wall. So at 50 miles an hour, how far are you going to go up that wall? Meanwhile, here we could ignore drag and friction for those wall maneuvers. Like maybe we're slowing down by 1 or 2 miles an hour, but for the most part, we're going to hit that curve at a given speed, and we could solve for like how fast, how high up the wall, right? So in these cases, I would say, like, even if I did want to say there is friction, there is drag, for the most part, I'm going to say, like, all right, for this problem, if I'm trying to figure out, like, how high up the wall the rider gets at 50 miles an hour, I don't really care that it's actually 49.5 by the end of the curve. It's just not. So then what about B? If we start taking into account drag and friction and the weight and the slope, like what is the slope of this thing? What are we asking there? What could we do with that? Yeah.
How would you be able to find like the acceleration or like the sum of the forces?
Yeah. So we could figure out like how fast is this person accelerating. For acceleration, because drag is always v squared, and you could say that the initial acceleration is only a function of normal force and weight, right? Because we would just have MA. Oh yeah, this was the other thing that people were trying to figure out. It's like, all right, I know there's like momentum, right? Like there's some kind of things are moving, and moving has a force. Like a hammer sitting still is not very good, but a hammer swinging, that can drive nails, can like bruise your thumb, can do all sorts of damage. So one way, this is my the highly recommended way, is like keep all the forces in your free body diagram. This is all the things causing motion. reaction forces, drag, friction, gravity, Coulomb, like electrostatic forces, like all that stuff, free body diagram. And then the only time you have like momentum or changes in momentum is in your kinetic diagram, where now I can say this is equal to MA. So MA is pointing down the slope. So now I know MA equals negative force of friction, negative force of drag. There's no normal force because it's normal to the motion, but plus that mg cosine. This is like mg sine theta. So the bigger the angle, the more acceleration down we have. And then same thing here. Like if I'm looking at this and mg, all that is going to be equal to like mv squared over r, like that. So I take all those ideas of like, hey, there's momentum, and the momentum is the thing keeping me up on the wall. That's equal to my acceleration this way. So it's, and the normal force and that mv squared are both pointed same direction. Right? Or is it pointing towards the center? Is it center of this thing? Now that I'm thinking about it, I feel like it's like this, right? Right? Because it's got to be around the curve. I think it's got to be center seeking of the bigger curve. That's what I think. Yeah.
In your MA, why isn't the normal force
In this right hand side, like kinetic diagram? So kinetic diagram is just describing mass times acceleration. So it's only in terms of like, is it a kinematic or a kinetic problem? Our MA, that kinetic diagram, is just a kinematic description. Like, in order for this thing to do what it needs to do, it has an acceleration. So mass times acceleration is my right hand side. My left hand side is all the kinetic parts of like, to create that mass times acceleration, I had a normal force, I had an mg force. Yeah. Does that kind of answer like why isn't the normal force on the right hand side? Yeah. You mean, are you asking about like, it'll catch up in a second, like this normal force? That one, because what I'm trying to say here is that so let's call this like angle alpha. Is that one gonna be cosine? Now I gotta like decompose things. Anyway, let's. But then how is gravity? How is this working? What am I doing wrong here? Because there's got to be something, right? Because it can't just be mv squared over r equals n dotted with I. I guess we have to solve for the components of n. Is that what I'm missing? But the main thing that I'm trying to separate is like sum of the forces equals ma. So the normal force is a force over on the left hand side. Now this is bothering me. What am I doing wrong? Does anybody see? Well, it's hard to do it with a crowd on the fly.
What is it you're trying to solve?
So if I'm trying to set up an equation of like mv squared over r equals like normal force and gravity depending on is it mg cosine, like if that's cosine like alpha in that case?
Yes.
Depending on how high up the wall you go?
Just, well,
Yeah.
yeah, that should be the normal force.
But the normal force and, but wouldn't it be equal and opposite? Because normal force is pointing that way, and mv squared over r is pointing that way too.
If the incline is this way, then normal force is pointing.
I guess then they're both equal. They're both equal to each other, right? Because they're both pointing in the same direction. Yeah. Something like that. Yeah, I think that's how we end up. If we dot with that, if I say like the normal force dotted with that I direction, get just the component along that x direction. I think that all works out. Could be wrong. It's happened before. Not to get into, yeah, now we're like diving into like solving problems rather than a free body diagram, but anyway, does that, I don't know if there's still a question about like why MA doesn't have a normal force in it. Did you still have a question about that? Or I can check in. Did I miss other approaches? Like, did you think about this in a different way? So one of the main things that I wanted to show is kind of like, they're both describing like different parts, different maneuvers, like parts of the race or maneuvers, like however you want to think about it. Like one is just trying to figure out like how fast can we go. Another one is trying to figure out like how fast can we go around a turn. And they're kind of two separate problems that we can think about, rather than trying to just like shove everything into one big like model of like, let me simulate the whole race all in one diagram. You can do that, but it takes a lot of like mental effort, and there's probably just like pieces that you can daisy chain together, and it's a lot easier to work on it that way. Kind of makes sense? Like, if you can, start simple. You can always make it a little more complex as you go. And then Now we've got 2.10. So copy this one over. This one we're told to make a point mass, like treat the rocket as a point mass. And then draw these like thrust, gravity, drag, and wind. So we have these different forces. What is a point mass? Why would you, yeah.
You're treating the whole system as a point.
Okay, yeah, so we're treating the whole, take this whole rocket, right? Try not to be too phallic. It's hard. So we're taking that whole like rocket, treating it just as one little point. What does that do to the rocket? What is it now saying? Yeah.
Like lose all the geometry and volume.
Sorry?
It's like the geometry to it and its volume. So you kind of have like a mass act on a force instead of component of a mass.
Okay. Yeah. So there's something like we're simplifying. It still has mass and volume, and those kind of things. Yeah.
Or is it more like the aerodynamics?
We're still like we're factoring in drag, so we are accounting for aerodynamics of the rocket. Like you can have a point mass, like in this case, like we have a point mass, and we are saying it has an area, a cross-sectional area. It has like a cross-sectional area to the wind. Like it has all these things. They're creating forces on a point mass, not forces on an object. What does that change for the object? Yeah.
If it's like just at one point as opposed to the whole assembly, you don't have to take into account like how like different forces are acting on different points of it.
Okay.
There's things like moment that depend on where on the object that the force is being applied. So
Yeah.
kind of like simplifies it.
So like wind force, let's say there's more like higher wind at the top versus the bottom, that's creating a torque. But if I say it's all a point mass, then sum of the moments is zero because all the forces go through the center of a point. You can't apply the force and create moment on that point. So here, when we so point mass assumption is great, but the main thing that you're losing is that there is no rotation, or that rotation doesn't matter. One of the two things is the base assumption there. Like a baseball, when you throw a baseball, whether it's spinning or not, has minor effects on like the actual motion of the baseball. So I don't really care what the torque on the baseball is. I just need total. I can do a point mass assumption. Say this is where it went. For a rocket, point mass, if it's not rotating, then that's probably a great assumption that it is all point mass work. But if you're worried about like how do I keep this thing steady while these different forces are acting on it, then maybe we would need like rigid body. because then we can say for a given moment, this thing is going to start spinning at a given rate. Cool. Okay. So let's try it out. Get those thrust and gravity, drag. Okay. Okay.
I was the worst shooting the bed. I knew the 5-point line was farther, but I couldn't get it down.
So main thing that I saw was kind of like we have thrust that's driving us up into the air. Drag is somehow opposing thrust. Opposing your motion, right? So technically we could be thrusting in one direction but actually moving somewhere else, but it's probably a good assumption that if our thrusters are pushing us this way, then the biggest drag component is that way. And then wind is probably pushing left or right. That's what I saw most of the time. Yeah, looking good. Yeah.
Does it matter where you draw the thrust arrow? It's technically from the bottom. Or should you just put that on the top?
So then when you have a point mass assumption, like vectors, you can move anywhere you want, and they're not creating any moment on the object. So I can put it on the top, on the bottom. I could take it and move it over here, but it's not creating any torque because it's all point mass assumption. This would just be a very awkward and weird place to put it, but technically I could, because vectors only have magnitude and direction, like their location doesn't matter. But yeah, top or bottom, it's okay. Cool. Yeah.
There's no normal force. There's nothing in contact.
Ooh, yeah, nice. So normal force, we get used to like drawing it like, oh, there's some kind of normal, but if you're not in contact with anything, like if you're actually taking off, then we don't need to say that there's a normal force because there's no contact to define that. In general, like normal forces they're constraint forces. So they're a force that exists to maintain some kind of geometry. So we solve for the motion, then figure out how big a normal force is, usually. Cool. We have 2 minutes, right? I keep getting mixed up because the last class is 55. We're 11, right? Ends at 11. But I think this is a good wrapping up. Call it a day. All right, thanks a lot.